Good evening and welcome to the White House. Tonight we are honored to have Professor Stephen Hawking deliver our second Millennium Lecture. I'd like to thank everyone who has made this evening possible, especially Ellen Lovell, the Director of the White House Millennium Council, the National Endowment for the Humanities and the State Humanities Councils, the community colleges, and especially Sun Microsystems, which is bringing this event to our fellow Americans and indeed to people around the world. First, via satellite to audiences at 190 downlinks in 43 states, and then to thousands and thousands more via the internet and C-SPAN and the BBC. Those wanting to watch this cybercast can click on the White House website, which is www.whitehouse.gov. I believe that we may have in this room the largest gathering of American physicists ever assembled at the White House. And I am particularly pleased to introduce two Nobel laureates, Dr. William Phillips and Douglas Osheroff. And I wish they would both stand so we could recognize them. I'm also pleased that a number of friends have joined us from Great Britain, including the president of Cambridge University, Sir Alex and Lady Brewers. And we're delighted to have Professor Hawking's wife, Elaine Hawking, with us as well. This lecture continues a series of Millennium Evenings with scholars, scientists, and other creative individuals, which we are holding to commemorate and celebrate this milestone. Over the next 3 years, we have a unique opportunity to take stock of who we are and who we want to be as a people, as individuals and families, as communities, as a nation, and as neighbors on this planet. The theme we have chosen for the millennium is Honor the Past, Imagine the Future. A few weeks ago, Professor Bernard Bailyn from Harvard University inaugurated this series with a talk about the ideals and challenges that shaped America more than 200 years ago and which continue to influence us today. Tonight, we leap beyond boundaries of historical time and place to hear from a man who has helped revolutionize our understanding of the universe and who will help us imagine the future of scientific discovery. The ongoing exploration of our cosmos reflects humanity's deepest longing for knowledge about ourselves and our universe. And as we enter this new millennium, we are obligated to keep pushing back the frontiers of science and discovery, to advance our pursuit of knowledge, and to apply what we have learned from the heavens to help improve lives here on Earth. We've invited students from area colleges and universities to join us tonight, not only because we know this lecture will inspire them, but also to stress the critical importance of providing our future leaders the best possible education in the fields of science and math. We have with us this evening a man who has spent a lifetime unlocking the mysteries of the universe. Almost 25 years ago, when Stephen Hawking was formally inducted into the Royal Academy in London, he signed his name in a book that bore the signature of Sir Isaac Newton on one of its earliest pages. He has since come to be recognized, along with Newton and other giants, as one of the most brilliant physicists of all times. Even as a young student, Stephen Hawking was drawn to science. "I always wanted to know how everything worked," he once said. He attended University College, that's at Oxford University, where my husband was also privileged to attend as a Rhodes Scholar, but then went on to Cambridge University to study cosmology, and in particular, the evolution of the universe. He has since applied his prodigious talents to seeking answers to the most fundamental of questions, such as where did the universe come from, and can we predict the future? Professor Hawking has received numerous honors, and we could not begin to recount all of them. But those honors stand for a lifetime of dedication and work. And in particular, those of us who are lay people are grateful to him because he has attempted to communicate with us. He's written books about the general public's understanding of recent scientific breakthroughs, such as the Big Bang Theory and the notion of an expanding universe. A Brief History of Time became the best-selling science book ever written. I have to confess there's much in it I still do not understand, despite my best efforts, but there are some heartening insights, and one of my favorites is where he writes, Present evidence suggests that even if the universe is going to recollapse, it won't do so for at least another 10,000 million years. And that certainly, I believe, gives us time to get things right once and for all. As many of you know, Professor Hawking developed ALS, what we commonly call Lou Gehrig's disease. It's a progressive motor neuron condition. But thanks to the wonders of science and technology, he will communicate with us tonight through a customized computer system. It enables him, by pressing a switch with his hand, to select words from the bottom of his computer screen, which is located on the arm of his wheelchair. When he's finished a sentence, he sends it to a speech synthesizer, which he jokingly complains has given him an American accent. Stephen Hawking embodies the enduring spirit of imagination that sees no boundaries, only possibilities. Tonight, we celebrate his life of study and accomplishment, his relentless curiosity, his wit, his optimism, his humanity, and his ability to expand the domain of physicists to audiences like us, inviting everyone to participate in the wonder and awe of the cosmos. It is a true honor and pleasure to introduce to you tonight Professor Stephen Hawking, who will speak to us about imagination and change, science in the next millennium. Professor Hawking.
Can you hear me? My theme tonight is Science in the New Millennium. The popular picture of science in the future is shown on television every night in science fiction series, like Star Trek. They even persuaded me to take part, not that it was difficult. Because of the red alert, I never collected my winnings. I approached Paramount Studios, but they didn't know the exchange rate. The Star Trek appearance was great fun, but I show it to make a serious point. Nearly all the visions of the future that we have been shown, from H.G. Wells onwards, have been essentially static. They show a society that is in most cases far in advance of ours, in science, in technology, and in political organization. The last might not be difficult. There must have been great changes, with their accompanying tensions and upsets, in the period between now and then. But by the time we are shown the future, science, technology, and the organization of society are supposed to have achieved a level of near perfection. I want to question this picture and ask if we will ever reach a final steady state of science and technology. At no time in the 10,000 years or so since the last ice age has the human race been in a state of constant knowledge and fixed technology. There have been a few setbacks, like the Dark Ages, after the fall of the Roman Empire. But the world's population, which is a measure of our technological ability to preserve life and feed ourselves, has risen steadily, with a few hiccups like the Black Death. In the last 200 years, the growth has become exponential, that is, the population grows by the same percentage each year. Currently, the rate is about 1.9% a year. 1.9% may not sound very much, but it means that the world population doubles every 40 years. Other measures of technological development in recent times are electricity consumption, or the number of scientific articles. They also show exponential growth, with a doubling time of 40 years, or less. Indeed, we now have such heightened expectations that some people feel cheated by politicians and scientists because we have not already achieved the utopian visions of the future. For example, the film 2001 showed us with a base on the moon and launching a manned, or should I say, personed, flight to Jupiter. I can't see us managing that in the next 3 years, whoever wins the election. There is no sign that scientific and technological development will slow down and stop in the near future. Certainly not by the time of Star Trek, which is only about 300 years away. But the present exponential growth cannot continue for the next millennium. By the year 2600, the world's population would be standing shoulder to shoulder, and the electricity consumption would make the Earth glow red hot. If you stacked the new books being published next to each other, you would have to move at 90 miles an hour, just to keep up with the end of the line. Of course, by 2600, new artistic and scientific work will come in electronic forms, rather than as physical books and papers. Nevertheless, if the exponential growth continued, there would be 10 papers a second in my kind of theoretical physics, and no time to read them. Clearly, the present exponential growth cannot continue indefinitely. So what will happen? One possibility is that we wipe ourselves out completely by some disaster, such as a nuclear war. There is a sick joke that the reason we have not been contacted by extraterrestrials is that when a civilization reaches our stage of development, it becomes unstable and destroys itself. Of course, it is possible that UFOs really do contain aliens, as many people believe, and the government is hushing it up. I wouldn't like to comment on that. Personally, I believe there's a different explanation why we have not been contacted, but I won't go into it here. However, even without that, there is a very real danger that we will kill everything on this planet, now that we have the technological power to do so. Even if we don't destroy ourselves completely, there is a possibility that we might descend into a state of brutalism and barbarity, like the opening scene of Terminator. But I'm an optimist. I think we have a good chance of avoiding both Armageddon and a new Dark Ages. So how will we develop in science and technology over the next millennium? This is very difficult to answer. But let me stick my neck out and offer my predictions for the future. I will have some chance of being right about the next 100 years, but the rest of the millennium will be wild speculation. Our modern understanding of science began about the same time as the European settlement of North America. In 1679, Isaac Newton, the second Lacazian professor at Cambridge, published his theory of gravity, and in 1864, Clerk Maxwell, another Cambridge man, discovered the equations that govern electricity and magnetism. By the end of the 19th century, it seemed that we were about to achieve a complete understanding of the universe, in terms of what are now known as classical laws. These correspond to what might seem the common sense notion that physical quantities such as position, speed, and rate of rotation should be both well defined and continuously variable. But common sense is just another name for the prejudices that we have been brought up with. Common sense might lead us to expect quantities like energy to be continuous. But from the beginning of the 20th century, observations began to show that energy came in discrete packets, called quanta. It seems that nature is grainy, not smooth. A new kind of theory, called quantum mechanics, was formulated in the early years of the 20th century. Quantum theory is a completely different picture of reality, so it should concern us all, but it is hardly known outside physics and chemistry, and not even properly understood by many in those fields. Yet if, as I hope, basic science becomes part of general awareness, what now appear as the paradoxes of quantum theory will seem as just common sense to our children's children. In quantum theory, things don't have a single unique history, as our present-day common sense would suggest. Instead, they have every possible history, each with its own probability. There must have been a history in which the Chicago Cubs won the World Series, though maybe the probability was low. However, for large-scale systems like baseball games, the probability is normally peaked around a single history, so there is very little uncertainty. But when one goes to the small length scales of individual particles, the uncertainty can become very large. For example, if one knows that a particle is at a point A at a certain time, then at a later time, it can be anywhere, because it can have any path or history. To calculate the probability that it is at a point B, one has to add up the probabilities for all the paths or histories that take it from A to B. This idea of a sum over all possible histories is due to the American physicist and one-time bongo drum player, Richard Feynman. The possible particle histories have to include paths that travel faster than light, and even paths that go back in time. Before anyone rushes out to patent a time machine, let me say that in normal circumstances at least, one cannot use this for time travel. However, paths that go back in time are not just like angels dancing on a pin. They have real observational consequences. Even what we think of as empty space is full of particles moving in closed loops in space and time. That is, they move forward in time on one side of the loop, and backwards in time on the other side. These closed loops are said to be virtual particles, because they cannot be measured directly with a particle detector. However, their effects can be measured indirectly. One way is to have a pair of metal plates close together. The effect of the plates is to reduce slightly the number of closed loops in the region between the plates relative to the number outside. There are thus more closed loops hitting the outside edges of the plates and bouncing off than there are hitting the inside edges. One would therefore expect there to be a small force pushing the plates together. This force, which was first predicted by the Turkish physicist Hendrik Casimir, has been observed experimentally. So we can be confident that closed particle loops really exist. The awkward thing is that because there's an infinite number of points in space and time, there are an infinite number of possible closed loops of particles. This infinite number of loops didn't matter in the calculation of the force between two plates, because the numbers between the plates and outside them are both infinite. There is a well-defined way in which one can subtract one infinity from the other and get a finite answer. It is a bit like the American budget. Both the government tax revenue and its expenditure are very large sums, almost infinite. Yet if one is careful, one can subtract one from another and get a small surplus, at least until the next election. Where the infinite number of closed loops caused trouble was when people tried to combine quantum theory with Einstein's general theory of relativity. This is the other great scientific revolution of the first half of the 20th century. It says that space and time are not flat, like common sense once told us that the Earth was flat. Instead, they are warped and distorted by the matter and energy in them. An infinite number of closed loops of particles would have an infinite amount of energy and would curl space and time up to a single point. To deal with this infinite energy requires some really creative accounting. The key concept was a new kind of balance or symmetry in nature, called supersymmetry, which was first proposed by two Russians, Gelfand and Lichtman, in 1971. The idea was that as well as the ordinary dimensions of space and time, with which we are familiar, there were extra dimensions that were measured in what are called Grassmann numbers. Of course, science fiction has been telling us for years that there are extra dimensions. But even science fiction did not think of anything as odd as Grassmann dimensions. Here the word odd has a technical use, as well as the usual meaning of peculiar. Ordinary numbers are said to be even, because it doesn't matter in what order one multiplies them. 6 times 4 is the same as 4 times 6. But Grassmann numbers are odd, in the sense that x times y is minus y times x. The existence of these extra odd dimensions implies that every species of particle must have a super-partner species. The super-partner species will also have closed loops of particles. But the energy of the super-partner loops will have the opposite sign to those of the original species. Thus the infinite energies tend to cancel out. But as the President knows, balancing the budget is a very delicate business. Even if one removes the main deficit, smaller deficits have a nasty habit of appearing. Much of the work in theoretical physics in the last 20 years has been looking for a theory in which the infinities cancel completely. Only then will we be able to unify quantum theory with Einstein's general relativity and achieve a complete theory of the basic laws of the universe. What are the prospects that we will discover this complete theory in the next millennium? I would say they were very good, but then I'm an optimist. In 1980, I said I thought there was a 50-50 chance that we would discover a complete unified theory in the next 20 years. We have made some remarkable progress in the period since then, but the final theory seems about the same distance away. Will the holy grail of physics be always just beyond our reach? I think not. At the beginning of the 20th century, we understood the workings of nature on the scales of classical physics, which is good down to about 1/100th of a millimeter. The work on atomic physics in the first 30 years of the century took our understanding down to lengths of 1/1,000,000th of a millimeter. Since then, research on nuclear and high-energy physics has taken us to length scales that are smaller by a further factor of a billion. It might seem that we could go on forever, discovering structures on smaller and smaller length scales. However, there is a limit to this series, as there is to the series of Russian dolls within Russian dolls. Eventually, one gets down to a smallest doll, which can't be taken apart anymore. In physics, the smallest doll is called the Planck length, and is a millimeter divided by 100,000 billion billion billion. We are not about to build particle accelerators that can probe to distances that small. They would have to be larger than the solar system, and they are not likely to be approved in the present financial climate. However, there are consequences of our theories that can be tested by much more modest machines. By far the most important of these is supersymmetry, which is fundamental to most attempts to unify Einstein's general relativity with quantum theory. This would be confirmed by the discovery of superpartners to the particles that we already know. The superconducting supercollider, the SSC, was being built in Texas, and would have reached the energies at which superpartners were expected. However, the United States went through a fit of feeling poor, and cancelled the project halfway. At the risk of causing embarrassment, I have to say I think this was a very short-sighted decision. I hope that the US and other governments will do better in the next millennium. I expect supersymmetry will be confirmed eventually by experiments at CERN in Geneva. But it won't be possible to probe down to the Planck length in the laboratory. We can study the Big Bang to get observational evidence at higher energies and shorter length scales than we can achieve on Earth. However, to a large extent, we shall have to rely on mathematical beauty and consistency to find the ultimate theory of everything. Nevertheless, I am confident we will discover it by the end of the 21st century, and probably much sooner. I would take a bet at 50-50 odds that it will be within 20 years, starting now. The Star Trek vision of the future, that we achieve an advanced but essentially static level, may come true in respect of our knowledge of the basic laws that govern the universe. But I don't think we will ever reach a steady state in the uses we make of these laws. The ultimate theory will place no limit on the complexity of systems that we can produce, and it is in this complexity that I think the most important developments of the next millennium will be. By far the most complex systems that we have are our own bodies. Life seems to have originated in the primordial oceans that covered the Earth 4 billion years ago. How this happened, we don't know. It may be that random collisions between atoms built up macromolecules that could reproduce themselves and assemble themselves into more complicated structures. What we do know is that by 3.5 billion years ago, the highly complicated molecule, DNA, had emerged. DNA is the basis for all life on Earth. It has a double helix structure, like a spiral staircase, which was discovered by Francis Crick and James Watson in the Cavendish lab at Cambridge in 1953. The two strands of the double helix are linked by pairs of nucleic acids, like the threads in a spiral staircase. There are 4 kinds of nucleic acids. I won't try to pronounce their names, because my speech synthesizer makes a mess of them. Obviously, it was not designed for molecular biologists. But I can refer to them by their initials, C, G, A, and T. The order in which the different nucleic acids occur along the spiral staircase carries the genetic information that enables the DNA molecule to assemble an organism around it and reproduce itself. As the DNA made copies of itself, there would have been occasional errors in the order of the nucleic acids along the spiral. In most cases, the mistakes in copying would have made the DNA unable to reproduce itself. Such genetic errors, or mutations, as they are called, would die out. But in a few cases, the error or mutation would increase the chances of the DNA surviving and reproducing. This natural selection of mutations was first proposed by another Cambridge man, Charles Darwin, in 1857, though he didn't know the mechanism for it. Thus the information contained in the sequence of nucleic acids would gradually evolve and increase in complexity. Because biological evolution is basically a random walk in the space of all genetic possibilities, it has been very slow. The complexity, or number of bits of information, that are coded in DNA is given roughly by the number of nucleic acids in the molecule. Each bit of information can be thought of as the answer to a yes-no question. For the first 2 billion years or so, the rate of increase in complexity must have been of the order of 1 bit of information every 100 years. The rate of increase of DNA complexity gradually rose to about 1 bit a year over the last few million years. But now we are at the beginning of a new era in which we will be able to increase the complexity of our DNA without having to wait for the slow process of biological evolution. There has been no significant change in human DNA in the last 10,000 years. But it is likely that we will be able to completely redesign it in the next 1,000. Of course, many people will say that genetic engineering on humans should be banned. But I rather doubt if they will be able to prevent it. Genetic engineering on plants and animals will be allowed for economic reasons, and someone is bound to try it on humans. Unless we have a totalitarian world order, someone will design improved humans somewhere. Clearly, developing improved humans will create great social and political problems with respect to unimproved humans. I am not advocating human genetic engineering as a good thing. I am just saying that it is likely to happen in the next millennium, whether we want it or not. This is why I don't believe science fiction like Star Trek, where people are essentially the same 400 years in the future. I think the human race, and its DNA, will increase its complexity quite rapidly. In a way, the human race needs to improve its mental and physical qualities if it is to deal with the increasingly complex world around it and meet new challenges like space travel. And it also needs to increase its complexity if biological systems are to keep ahead of electronic ones. At the moment, computers have an advantage of speed, but they show no sign of intelligence. This is not surprising, because our present computers are less complex than the brain of an earthworm, a species not noted for their intellectual powers. But computers obey Moore's law, put forward by Gordon Moore of Intel. This says that their speed and complexity double every 18 months. It is one of these exponential growths, which clearly cannot continue indefinitely. However, it will probably continue until computers have a similar complexity to the human brain. Some people say that computers can never show true intelligence, whatever that may be. But it seems to me that if very complicated chemical molecules can operate in humans to make them intelligent, then equally complicated electronic circuits can also make computers act in an intelligent way. And if they are intelligent, they can presumably design computers that have even greater complexity and intelligence. This is why I don't believe the science fiction picture of an advanced but constant future. Instead, I expect complexity to increase at a rapid rate, both in the biological and electronic spheres. Not much of this will happen in the next 100 years, which is all we can reliably predict. But by the end of the next millennium, if we get there, the change will be fundamental. Lincoln Steffens once said, "I have seen the future, and it works." He was actually talking about the Soviet Union, which we now know didn't work very well. Nevertheless, I think the present world order has a future, but it will be very different. Mr. President, First Lady, this is my view of science in the next millennium.
Thank you very much. And Dr. Hawking, you'll have to forgive me, I'm a little hoarse. I hope for some genetic improvement sometime in the next year or so. Ladies and gentlemen, this was a stunning event for me, and I hope for all of you. Yesterday, Stephen and Elaine came by the White House to see Hillary and me, and as you can imagine, like Hillary, I had reread A Brief History of Time, and I was utterly terrified that he would say something like, you know, I went to University College, Oxford, too, and then he would ask me some incredible comparative academic question about our experiences there. Instead, he said, was the food just as bad when you were there? Which was a wonderful relief. Albert Einstein once said, because politics is for the present, but an equation is something for eternity. Equations were more important than politics. I don't know about the politics part, but Professor Hawking's insights into equations have altered our notions of time and the very nature of eternity itself. Tonight he's given us a lot to think about. Even the ability to imagine a future in which we as humans will have finally captured the holy grail of physics, reconciling the infinitesimal with the infinite, presenting the world with the ultimate theory of everything. Now, when a physicist does that, he can totally ignore politics and buy a newspaper. Think about it. The one thing I liked most about thinking about the future in Professor Hawking's term is that even when we reach the era of Star Trek, which will make a lot of our children very happy, it won't be so static. It will still be human and dynamic. And according to the visuals accompanying the lecture, it will still matter whether you can bluff at poker, which is encouraging. I want to get on with the questions now. And again, I want to thank Professor Hawking for the extraordinary clarity and vigor of his presentation, and for sharing his time with us tonight, and for placing this particular moment in the larger spectrum of time, which I think if we all could do more and more clearly every day, we would live happier, more productive lives. Thank you, Professor. Ellen, would you like to take over and bring in the question?
Thank you, Mr. President. I'd like to begin our question and comment session. Because of the way Professor Hawking communicates and the time it takes him to select words from his screen to assemble his responses, we did give him a few questions in advance. I just learned that we're getting 2 emails a minute from all over the world and have over 300. The students who are here tonight and in the Indian Treaty Room were chosen on the basis of the questions they wrote to Professor Hawking. But for the first live question, I turn to Dr. Vera Rubin, astrophysicist in the Department of Terrestrial Magnetism at Carnegie Institute.
Thank you, Professor Hawking, for this most stimulating and entertaining talk. Our knowledge of the universe comes both from observations and from theoretical studies. I wonder if you would be willing to stick your neck out once again and tell us what you think will be the most exciting discovery in connection with cosmology in the next 100 years.
And while Professor Hawking is responding, I want to turn to Dr. Sylvester Gates, past president of the American Association of Black Physicists, to expand on a point Professor Hawking made. Dr. Gates, for the average listener like me, how do super partner species and closed loops of particles cancel each other out? This is advanced physics in 2 minutes. Microphone?
Well, first of all, as we all know, we can't walk through walls. It's a very obvious property. Don't have to teach any student a physics course to know that. And the idea of supersymmetry, where we think that there's another part to the universe that we haven't seen, there may be objects for which this isn't true. There may be things, the super partners, and we don't know how much they are, how many there are, or how they behave. But if they're there, they lead to new forms of energy and matter, and the possibilities are beyond our imagination at this point. Thank you.
I think I got it. We got an intriguing question from a University of Maryland student, Daniel Manilow, which I'd like to direct to Dr. William Phillips, 1997 Nobel laureate in physics. Dr. Phillips, why does the universe obey any laws at all?
Well, that's a really good question, and I really wish I had a really good answer for it. It's the kind of question that has intrigued and vexed scientists and I suppose philosophers and theologians for a long time. It's really quite remarkable. All of the wonderful things that Professor Hawking talked about can actually be described in a very small number of relatively simple equations and then a lot of complicated mathematics. Why is it that the universe is so simple? Why is it that it follows mathematical laws? Well, people have speculated about this, and one possible answer is that if the universe had been any different from what it is, we wouldn't be here. That is, if the laws of the universe hadn't been what they are, or if there were no laws at all, it would have been impossible for life to have evolved. It would have been impossible for us to have evolved to the point that we could ask that question. So that's sometimes called the anthropic principle, not perhaps to put too much emphasis on people, but it probably applies to amoebas as well, that they wouldn't have been able to evolve either. On the other hand, there is another answer which isn't actually that far from that answer, and if you're a person with religious faith, as I am, you could answer that the reason we have a universe that follows laws is because God decided to make the universe in that way, because God wanted us to develop the way we have and to evolve in the way that we have, and that this is of course a philosophical and theological answer, and it has more to do with one's faith than one's scientific conclusions, but it's an answer that I like very much and that I don't find very different from the first one.
Thank you. Professor Hawking raised the question of redesigning our DNA. Dr. Francis Collins, head of the Human Genome Project at the National Institutes of Health, is here. Dr. Collins, what would be the implications of genetic engineering of the human race?
Well, I appreciate the question, and certainly Professor Hawking's presentation was very thought-provoking in this regard. Having physicists speculate about biology is welcome indeed. No, I mean that. Certainly the proposal about the widespread application of genetic engineering to human beings raises a couple of points. This kind of knowledge is in itself neither good nor evil. It's knowledge. It's the use to which we put it that determines sort of the moral character of it. To what extent are these improvements in human beings moral or immoral is a question that we as society will have to wrestle with. If in fact the goal is to wipe out a dread disease, then I think that's entirely consistent with our moral obligations as human beings to try to alleviate suffering. And if that could be done without inducing other harms, then I suspect many of us would celebrate it. If, on the other hand, it is to achieve improvements, you quickly begin to wonder who defines what an improvement is. And does that in fact allow one group of people to decide that their characteristics are more improved than others and therefore more in need of being transferred to various recipients? And that puts one into a bit of an ethical dilemma. Furthermore, I think, as the President has recently said, science should not be a line that allows us further to discriminate between the haves and the have-nots. And one would worry very much about a technology which allowed this kind of improvement only to be available to certain people. Finally, and I echo what the preceding speaker said, this does get us into an area where you begin to wonder about our view of ourselves, especially our view of ourselves as it relates to God. If we are to transform our species in this wholesale way, what do we end up with? So there's plenty of things to think about there. I actually, along with Winston Churchill, have a great deal of confidence in our ability as a species to make sure that our technologies are our servants and not our masters, but it will take a great deal of public involvement to make sure that that is the outcome.
Thank you very much. We're ready for Dr. Hawking's reply to Dr. Rubin.
The most exciting discovery will probably be something we don't expect. It is such surprising discoveries that has led to the great revolutions in the past.
We have a question from the internet.
This is a question from Kendra in Washington. Do you ever lose your place while solving mathematical equations in your head? And if so, how do you handle that?
It is difficult to handle complicated equations in my head. I therefore avoid problems with a lot of equations, or translate them into problems in geometry. I can then picture them in my mind.
This question is from Larry in Denver. How does it feel to be compared to Einstein and Newton?
I think to compare me to Newton and Einstein is media hype.
Must say you did look good at the card table
I
with
fit the
them.
popular stereotype of a mad scientist, or a disabled genius, or should I say, a physically challenged genius, to be politically correct. I am clearly physically challenged, but I don't feel I'm a genius like Newton and Einstein.
Mrs. Clinton, there is a special message for you, the President, and Professor Hawking.
And is that message on the internet?
You're going to see it on the screen behind you.
Okay.
It comes from very far away.
Oh, this is a special message, Professor Hawking, from your friends in outer space.
Good evening, Mr. President, Mrs. Clinton, and Professor Hawking. My name is Andrew Thomas. I'm the NASA astronaut presently orbiting the Earth on the space station Mir. I want to thank you for the opportunity to join you briefly tonight as I explore the universe up here on the space station, the universe that Professor Hawking has so clearly elucidated to us in his writings. I'm delighted that students are able to participate in this event. It gives us a way of honoring the past and imaging the future. And encouraging students in these activities, I think, is the future for us. Thank you all very much for your participation, and good evening.
Well, I have to bring us back to Earth. Sakil Moyo from the University of the District of Columbia. I know you have a question.
Where are they at? Oh.
Hi, my question to Professor Hawkins is, if you believe that the galaxies around the universe will collapse once again, do you predict this as being another Big Bang?
We don't yet know how much matter there is in the universe. The observations at present suggest that there isn't enough matter to stop the expansion of the universe, and so it will continue to expand forever. But if there is extra dark matter that we haven't detected, the universe could collapse again to a big crunch. However, the big crunch would be the end of the universe, and of time itself. There doesn't seem to be any way one can continue through the big crunch to a new Big Bang. But don't worry. The big crunch won't come for at least 20 billion years. That will last my time, and even that of the president, who is a bit younger than me.
Dr. Andrea Dupree, I'm going to put you on the spot for a short comment on the lecture.
Thank you. Well, during this marvelously eclectic and imaginative lecture, I couldn't help but think about the enormously rapid pace of our understanding and our development in things that we couldn't even anticipate. I know when I started out in training as an astrophysicist, I never thought that I would be able to use the Hubble Space Telescope to actually look at the surface of a star where the light is coming to us when Christopher Columbus arrived in our country. These just wonderful things that we've been able to do. And I really draw from much of this that we really have to prepare for the unexpected. And that's what basic research is all about. That we are looking for things and we're not always sure what we're going to find other than a magnificent, better understanding of where we are and who we are and where we are going. And I'm sure if we keep up the momentum that we've heard about tonight, that the next millennium will be magnificent and we'll have wonderful scientific rewards.
Another optimist. Thank you. Mrs. Clinton, the last question comes from the internet.
Oh, this question is from Al in New Hampshire. That is for our British guest, Al Gore, who is never without his computer and therefore can log on anywhere, and was very sorry that previous obligations kept him from being here. So here is Vice President's question. Within the past month, we have seen evidence suggesting a strong repulsive force in the universe, an anti-gravitational force causing the universe to expand surprisingly at an accelerating rate. How surprised were you by this finding? What are its most important implications? And how could your National Cosmology supercomputer help to prove or disprove these implications?
What the Vice President is referring to is some observational evidence that suggests that there may be an anti-gravitational force that would cause the universe to expand at an increasing rate. The existence of such an anti-gravitational force is very controversial. Einstein first suggested it might exist, but later regretted it and said it was his greatest mistake. If it is there at all, it must be very small. It is difficult to understand why it should be so small, unless it were exactly zero. We probably won't know if there is a small anti-gravitational force until observations come in from new satellites that the US and Europe will put up in the first years of the new millennium. To do the data analysis of these satellite observations will require a supercomputer like the National Cosmology Computer we have in Cambridge. If it turns out that there really is an anti-gravitational force, it will mean that inflation is a law of nature.
Dr. Hawking, our position is we have repealed that law. Let me say, first of all, in defense of my vice president, you will all understand that he would love to be here, but there is a peculiar gravitational force in New Hampshire that manifests itself with a remarkable regularity. Let me also say that in the visual presentation accompanying Dr. Hawking's lecture, there was that remarkable project stamped canceled on it. This administration opposed the cancellation of it, I'm proud to say. But we hope that the Swiss project will take up the slack. There are so many questions I know you would all like to ask. We have hundreds of questions coming in. And one of the questions I wish there were time to explore is if we do, in fact, acquire a general understanding that time and space are more multidimensional than we had imagined, and computers become ever more sophisticated, even if people will never be able to travel at the speed of light, will we be able to communicate someday in some ways that destroy our common notions of time? I thought about it a lot, and I'm not smart enough to know what the answer is, but I'd love to. That's one of the reasons I enjoyed rereading the book. Let me also say one other thing to close, since our Nobel laureate talked about his faith about how the world began. The First Lady started tonight by talking about the marvels of technology which enabled this astonishing man to communicate with us. And it is true that he is here and we did this because of the marvels of technology. It is also true, in my mind, that he is a genuine living miracle because of the power of the heart and the spirit. And we can only hope that all the advances that he has foreseen for us tonight in human knowledge will serve to amplify the heart and the spirit that we have humbly witnessed this evening. Thank you. And God bless you all.